In the last video, we talked about surface integrals of functions, and in this video, we're going to talk about surface integrals of vector fields. And before we do, we have to discuss a little bit of information about orientation, because there's positive and negative orientation for surface integrals. So there are, if I can get this thing to work, there are two orientations, and they have to do with the surface that we're looking at. So let's say that we have some surface that, I don't know, goes like that. In the back, that's in the back of it. Okay, so I don't know what that thing is. Some sort of a three-dimensional blob. If the normal vectors point away from the surface, so if the normal vectors, I'm just going to draw a few different examples of normal vectors along this blob. So if the normal vectors point outward, then that is considered positive orientation. If the normal vectors point inwards, let me see if I can draw a few different inward directing normal vectors on this blob. So there's some inward pointing normal vectors. Those are inward. Then the orientation is negative. So negative orientation. And if the orientation is positive, then we just take the surface integral and it will be positive. If the orientation is negative, then we'll multiply our surface integral by a negative number. Okay, so there's a little bit of background information. Now I guess let's go ahead and talk about what surface integrals of a function would look like. So notation for these. Notation looks like double integral of a vector field dotted with a change in a surface over S. So this is just notation for it. We can calculate these as a double integral of S of a vector field dotted with the normal vector, ds. Okay, now notice the difference here. The first one has a vector for S. The second one is just a differential of S. And these are different. The first one is just notation to say, hey, we're just going to find a surface integral of a vector field. And really what we're doing here is calculating the flux. And so for instance, if our vector field was, say, some sort of like a water, and it was going through a fishing net, that would be our surface. We are going to calculate that fluid motion through the net. So it has to be something that would go through the surface. So the flux of the vector field through the surface, S. All right, so this one is one way to do it, but you have to know the normal vector. Most surfaces have infinitely many normal vectors. The surface that I've drawn up above, the normal vector isn't constant the whole time, and so this would be very difficult to do with this specific example. The only place I can think of where I really use this first one is if I'm looking at if we're dealing with a plane. So if we have a plane, then we know the normal vector, and then we can use this one. The other thing that's difficult about using this second integral is not only do you have to apply this dot product to it, but after you do that, you then have a surface integral of a function. So you then have an integral of a function, ds, a surface integral of a function. And this takes us back to the last video. So it's kind of a two-step process in using the normal vector. All right, so starting with formula. So I'm just going to write down the formula with that normal vector again. So this is for a surface integral. We take the vector dotted with the normal vector ds over a surface. Now, if I have my my surface as an r of u and v, then I could write down each different normal vector as r sub u cross r sub v. A cross product finds a vector normal to that surface. So if I now apply this surface integral of a function, I'm going to have the double integral over my surface of the vector field dotted with, I want to make it a unit normal vector so that it's not scaled. So I'm going to dot it with r sub u crossed r sub v divided by the magnitude of r sub u cross r sub v. There's our unit normal vector. Then I want to multiply this by the ds part of it, which goes back to the last video. And if, on the last video, we had our surface being described by a vector function, we would multiply our function by the magnitude of r sub u cross r sub v dA. So at this point, our r sub u and r cross v, the magnitude of those can cancel. So another way that we can evaluate the flux of f across S, or evaluate this surface integral of a vector function, is to take the vector field and dot it with r sub u cross r sub v dA. Right, so we can just take a cross product of the vector function that represents the surface. So this one we would use if we are given a parameterization for the surface. All right, so the next step, we have one more formula that we can use, and this is if we're given a z equals a function of x. So if z equals some function of xy, we can write r, we could parameterize this surface and let x equal x, y equal y, and z equal that function of xy. So now if I find r sub u, I'm sorry, I don't have a u in there. Let's try to find maybe r sub x. How about it? So if I find the partial of this with respect to x, that would be, I'd have a 1 and then a 0, and then I'd have to take the partial of this function, whatever function z is with respect to x. If I take the partial with respect to y, I would get 0, 1, and then we would have to take the partial of f with respect to y. Now if I cross these two, r sub x cross r sub y, I would get, so let's see, for the x component I get 0 minus the partial of f with respect to x. So minus partial of f with respect to x. For the y component, I get partial of f with respect to y minus 0, but that is a negative component. So negative partial of f with respect to y. And then for the z component, I get 1 minus 0. So just 1. And then we have to put a little vector symbol. There we go. Got it on there. Okay, so now we have the cross product. I am going to now apply this formula to it. So I am going to take the double integral. I'm going to write my vector field in terms of its three functions, p for the x component, q for the y component, and r for the z component. And now I'm going to dot that with the cross product that I just found, the partial of f with respect to x, the negative partial of f with respect to y, and 1. And I get the double integral of negative p times partial of f with respect to x minus q partial of f with respect to y plus r dA. All right, so we have 3 different formulas that we can use depending on what we're given. If we have just a normal vector, we could use that guy. Then we would have to go and use the formula for vector fields of a function. If we are given the surface with an r of u and v with a vector function, we could use that. If our surface is a z equals a function of x and y, then we could use this guy. And if you look at the formula sheet for the test, all 3 of those are written on there under finding surface integrals of vector fields. Okay, I think it's time for an example. So let's find the surface integral. So actually, let's find the flux. Let's find the flux of f, which is, let's set our vector field equal to x, y, and z to the 4th. And so we're going to find the flux of that vector field across the surface that bounds the cone. That bounds the cone z equals the square root of x squared plus y squared beneath z equals 1, oriented inwards. Oriented inwards. Okay. We have a vector function, and we have z equals. So for this one, I'm going to use that last form that we had, the negative p times partial of f with respect to x, etc., etc. I'm going to use that form. But, well, just for giggles and just to show you how it works, we have a z equals here on this one. Oh, I also have to describe why we have 2 surfaces. We'll talk about that in a second. So we are going to have 2 integrals. And for this one, I am going to use the form with the normal vector, just to show you how that works too. All right, so if we draw this cone that is our surface, and the surface bounds the cone beneath z equals 1. And so maybe this isn't the best way to state it, but what I'm getting at there is there are 2 different surfaces. The cone itself is one surface, and then we also have the plane. And so because we have a solid shape that is bounded, we are going to have to do 2 different surface integrals on this. So you have to read into the problem very carefully to determine exactly how many surface integrals we have. How many surfaces are we looking at? All right, now this is oriented inwards. So as far as the normal vectors go, The normal vector for the z equals 1, if it's oriented inwards, is going to point downwards. The other ones are going to point in from the cone, kind of all the way around it in a circle. All right. And remember that positive orientation, it was the normal vectors were pointed outwards. All right, so let's look at, we'll do the cone first. And for the cone, I said I was going to apply this formula of negative p times partial of f with respect to x minus q times partial of y, f with respect to y, plus r dA. So I'm going to apply that formula for the first one. Okay, so double integral here. P is the x component of the vector field. So in this case, it is x. So negative x times the partial of f with respect to x. And in this case, z is equal to f. So f of xy is that square root function. So if we take the derivative of that square root with respect to x, we get, on the top we'll have 2x, and on the bottom we'll have 2 times the root x squared plus y squared. Minus q. Q is the y component of the vector field, which in this case is y. And then we have to take the partial of the function, which is that root, with respect to y. So that would be 2y divided by 2 times the square root of x squared plus y squared. Now we add r to it, and r is that is going to come from the z component of the vector field. And so in this case, that is z to the 4th, and we know that z is the square root of x squared plus y squared to the 4th. Notice that everything I've done was just with that cone. Haven't done anything with the z equals 1 yet. All right, so now this is a dA. And if we were to just look at the cone and we're just project that cone onto the xy plane, we would see a circle. And because z is equal to 1, that circle has a radius 1. And hopefully you are thinking now polar coordinates. Okay, so we want to transfer this all into polar coordinates. I'm going to simplify some things first here. 2's cancel. 2's cancel. So we would get a double integral of negative x squared minus y squared all over the square root of x squared plus y squared plus x squared plus y squared squared. One of the square roots in that fourth one of the squareds got rid of the square root from that fourth power. All right, now I'm going to go to polar coordinates. So on the top here, I'll have negative r squared. I'll have the square root of r squared, which is r, plus r squared squared, and all of that I'll have to multiply by r dr d theta. R is going to go from 0 to 1, theta from 0 to 2 pi. Okay, so this would be the same as the integral from 0 to 2 pi d theta. I can separate these. I've got r's and thetas separable or separated, and I've got constants in my integrals. So I can, in the bounds of my integrals, I can separate these. Integral from 0 to 1 of, so here if I divide by r, I've got an r and multiply by another r, so that would be a negative r squared. and then plus, I've got r to the fourth times r, so that is r to the fifth, and I still have to integrate it. The integral of, well, 1 with respect to theta is theta. Integrate it from 0 to 2 pi, and you get 2 pi. Times negative r cubed over 3 plus r to the 6th over 6. Evaluate it from 0 to 1. So we'll get 2 pi times negative 1/3 plus 1/6. And then this is 2 pi times, what do we get there? So 6, so negative 1/3. Right? Why does that seem off to me? 6, 2. Nope, I got it. Okay. And so this is equal to negative 2 pi over 3. Now, I have forgotten, luckily I remembered, a very important step in all of this, and that is the fact that those normal vectors pointed inwards for the cone. So on all of this, I've got to include a little negative sign out in front of all of it, which really, at the end of it, makes it positive 2 pi over 3. All right, so far we have found the flux of that function across the surface of the cone, but we still don't know what it's doing across the surface of the plane z equals 1. So let's do that next. Let's try to add to this. Okay. All right. So on this one, I said that 1/3 plus 1/6 is 1/3, and I am not sure that that is true. I think I made a mistake there. So 1/3 is 2/6, and add 1/6 to it, and we get negative 1/6. That should be a 6, and so at the end of all of this, we should get pi over 3, and not 2 pi over 3. Okay, back to the next. Okay, so now I kind of have to remember the problem. All right, we had the vector field was, I have to look it back up, x, y, and z to the 4th. And we were looking at that surface, z equals 1, and our big picture was this cone and that plane z equals 1. So for this one, I want to use the normal vector. Now, if you remember back to what that picture looked like, the normal vector of this surface, z equals 1, because the shape is pointing inward, that normal vector is pointed down. So that normal vector we could write as 0 in the x, 0 in the y, and negative 1 in the z. Now, if I apply my formula and my surface integral, so I'm going to dot the vector, I'm going to dot the vector field with the normal vector. And then I still have to think about this ds. So let me dot that first. So x, y, z to the 4th. I'm going to dot that with the normal vector 0, 0, negative 1. So if I do that dot product, I get 0 plus 0 minus z to the 4th ds. Now I have a surface integral to look at. Okay, so if I go back to the formulas for finding the surface integral just of a function, I either have to have a parameterized function or I have to have a z equals, and I happen to have a z equals in this. So now my formula tells me that I'm going to take the integral of the function evaluated at x, y, and z. So if I evaluate that function when z is equal to 1, I get negative 1. I get negative 1 to the 4th. Then I have to multiply that by a square root of the partial of z with respect to x. Well, there's no x in there, that's 0, and square that. The partial of z with respect to y, well, that's also 0, there's no y in there, and square that, plus 1. dA. So really what I now have is a double integral of negative 1, because that's a square root of 1, which is 1. Now to the bounds. Now for the bounds, we're once again looking at the same exact circle in there. So, and I can use the fact that I know that the double integral, so I know that the double integral of 1 dA is area. And in this case, my area would be pi r squared, and in this case radius is 1. So using that, now of course you can integrate with dr d theta and go from 0 to 1 and 0 to pi, but or 0 to 2 pi, you'd get the same thing. But using this fact that we know that a double integral of 1 is area, then I know that this double integral, because of the negative, is just going to be pi, negative pi. So for this part, I get that then the double integral of negative 1 dA is going to equal negative pi. And now we have to bring this back together. We've got to take surface 1, add it to surface 2, and that will give us our full surface integral. So for surface 1, our answer was, what did we end up getting there? 2 pi over 3. And I'm going to subtract pi from that. So I am going to subtract, let's see, 3 over 3 pi. So it looks like we should get negative pi over 3. Okay, it looks like this video just cut out on me. So I'm gonna start from here, and I guess, yeah, I'm just gonna keep going here. All right, we found that the area was pi, and now what I need to do is add together, I guess I need to finish up this. This one, then, of negative 1 dA, we would then get that that integral is negative pi. All right, so now I need to take surface 1 and add surface 2 to it. Now, I want to go back and mention something about surface 1 because I found a mistake. Okay, I think this is keeping going. All right, so our surface 1 we got was pi over 3. And then we're going to subtract pi from that. So if we subtract 3 over 3, we're going to get negative 2 pi over 3 as our final flux across the surface. And what it means is as this surface, as this vector field flows through this sort of a shape, it has a tendency, let's see, the normal vectors are pointing inwards. And so it has a negative flux with it, a negative tendency with it. Okay, so I think that gives you an example of all different kinds of surface integrals of vector fields. And the next thing coming up, we'll do a couple of special theorems with surface integrals.